the last speaker will be Professor Erik Hoel, who is widely known about as a founder of the causal emergence. And Erik Hoel is an American neuroscientist and psychologist and a fiction writer. So his main areas of research are the study and psychology of the consciousness, cognition, biological function of dreams, and the mathematical theories of the emergence. So Erik Hoel has done a lot of amazing works about the causal emergence. And today he will give us a talk entitled "A Framework for Effectively Measuring the Causal Emergence," TBC. So now it's time for the Professor Erik Hoel to give his wonderful talk.
Wonderful. Thank you all for inviting me to this conference. Unfortunately, I'm 12 hours difference, right? As always with Beijing. So I missed some of the first talks, but I can't wait to see the recordings and go through a lot of the research that you've been doing over here. I think is really fascinating. With that said, I want to talk about causal emergence, maybe more very, very generally, and particularly around this question of how science itself got its scale. So science operates at particular scales, and I'll talk about that. But I also want to say that I've been working on a second book, which is coming out about causal emergence. So this is coming out from Simon & Schuster, which is a big American publisher, July 25th. So it's coming out this summer. And it's both about causal emergence, which, as everyone has heard by now, is a mathematical theory of macro scale causation and how to find natural scales of descriptions in systems. And this book is also about a topic that's related in some ways, but is also a little bit separate. And that's this notion of what I call scientific incompleteness. And it's the idea that self-reference creates epistemological holes in science that are similar to Gödel's theorems. But these holes are in science rather than in mathematics. And the most notable example of this would be the difficulties around solving the problem of consciousness. But today we're just going to talk about the first part. And you know, if you actually want to find out sort of the latest of what I've been working on for causal emergence, please check out the book. This talk will be a bit of a preview of some parts of the book, particularly the parts that are sort of framing and introducing and refining the notion of causal emergence itself in as rigorous a way possible. And my hope is, of course, that it gets translated at some point. That would be it would be wonderful to have a Chinese translation of this book at some point. So we'll see, but that would be wonderful. So jumping right in, I think it's really useful when talking about emergence, rather than talking about some philosophical problem or mathematical problem, to start with a more practical problem, even if it is very large in scope. And that is, how did science get its scales? So if you look across the subdisciplines of science, what you'll find is a set of fields that are all stacked on top of one another in terms of their spatial scale and in terms of their temporal scale. So if we have something like atomic physics, maybe there's something underneath atomic physics, right? But atomic physics is some macro scale of whatever's underneath it. Maybe that's strings or so on, right? People debate. Chemical interactions are the macro scale of atomic physics. Biological cells are the macro scale of chemical, right? And this is a very simplistic sort of representation of this, right? You could draw hundreds of different fields and their different spatial temporal scales and how they interact, and it might look a bit more like a web than like a ladder, like here. But for now, let's assume that it is indeed a ladder and scales supervene on one another on top of the ladder. And the question is, why does science at all look like that? And it's a good question because, if you could imagine like a race of alien superintelligences who are all just committed reductionists, and who can somehow, through some magic, model the world at the most fine-grained microphysical level that they want. And I think that a lot of people have the instinct that if this were true, these aliens wouldn't miss out on anything. They wouldn't be missing any sort of knowledge, and they would never care about any sort of macro scale. They would just talk about and refer to and intervene on and experiment on solely microphysical states. It would be like if their language only included atomic physics. Of course, that's impossible because of the issues around compression and complexity. But we can sort of imagine a case like that and ask, well, would they be missing anything? And the issue, if you give the answer of they would be missing something, and that thing that they would be missing is compression, that it's easier to talk about and refer to and publish papers on biological cells just because they are compressions of microphysical events. And I mean compressions in an information theoretic sense. I mean compressions as in like a summary, or like the way that temperature is a summary, right? Scientists should seemingly want to avoid compression because compression is throwing out information. So this would imply that the best scientists, right, would be these super reductive hypothetical aliens. And we sort of are forced into having all these different scales of science solely because we're not sort of smart enough and don't have a large enough memory to actually refer to and talk about microphysical states. We would always want to be talking about as low down in the spatial temporal ladder of science as possible. And I think that is incorrect. So I think that there really are advantages that pop up at macro scales. And I think that that's likely due to causal emergence. So, but before we get into that, what I want to do is present a very simple model, a very simple mathematical model that looks somewhat similar to what we would expect this ladder of science to look like, but simplified to an incredibly radical degree, such that we're just talking about simple states and elements in systems. So first, we have to be clear on what I even mean by a macro scale versus a micro scale. So it's actually very useful to use a term here that's from analytic philosophy because it's very broad, and then you can create a mathematical formalism of it later. But the broad notion of the relationship between higher level scales and lower level scales is that of supervenience. So when A supervenes on B, what that means is that if all the facts about B are fixed, then everything about A, all the facts about A are also fixed. So the meaning of words supervene on their letters. So if I fix all the letters in the right way, the meaning is also fixed now. A painting supervenes on the brushstrokes. So if I do all the brushstrokes of a painting, I now have the macro scale of the painting. And Superman supervenes on Clark Kent because they're the same person. And one way to think about it is that there is no way that there can be a difference in B without some difference in A automatically. So if Clark Kent dyes his hair, then Superman has also dyed his hair, just automatically because they're the same person. If a painter changes a painting, they have to change something about the brush strokes. Right? You can't somehow change how a painting looks, presuming it's actually painted. You can't change how a painting looks without changing something about the brushstrokes. And similarly, if you change the letters around in a word, like if you take dictionary, the letters of dictionary, and you rearrange them to be indicatory, then you've also changed the meaning of the word because the meaning supervenes on the letters. So in this case, higher level macro scales supervene on lower level scales, in that I can't have a difference in, let's say, the state of some biological cell without there also being a difference between the atomic physics. By the way, can anyone see my cursor? If anyone wants to chime in, if they can actually see my cursor or no, that would be helpful for me to know if people can see what I'm pointing at. If not, that's okay. All right, so supervenience might seem like an obscure sort of logical entailment, but it also happens to describe really well the relationship between macro scales and micro scales. So macro scales supervene on micro scales. As I said, there cannot be a macro scale difference like a temperature change without some micro scale change, which is something changes about the particles, right? They move into some sort of different configuration, or have, you know, some sort of different kinetic energy or so on, right? And meaning that, you know, all the scales of science can be treated like this. So presumably your psychological state supervenes on your brain state, which supervenes on the molecular machinery of your cells, which in turn supervenes on your atoms. And the ladder of science is actually a ladder of supervenience. Okay, so how can we talk about supervenience in macro scales in really, really simple systems? Because I think that when people talk about emergence, one of the most dangerous traps is to describe very high level complex phenomena and then see if you can find examples of emergence in them. And it's not that it's automatically wrong to do that. It's just very dangerous to do that because it's very difficult to actually know all the full details of what's going on in those systems. So you might be missing something or misdescribing something. So I really prefer to work with extraordinarily, almost toyish examples, because that means that we know all the information. And so we can very clearly track, like if you can show a case of emergence in a very simple system, then it becomes undebatable because the system is so simple that you can go in and you can calculate it yourself and you can understand it and see it, versus if you're talking about very complex phenomena, then there's always sort of these extra factors that you have to take into account. So I prefer to work in really simple systems like Markov chains or Boolean networks or so on, or you might call them causal models. So how do we formalize supervenience across scales? So here's an abstract example of a system, which is here just two nodes, A and B on the left, and a macro scale of that system, which is, we'll call alpha instead of A and B, right? So alpha just is A and B. Nothing has been added or anything like that to alpha. It's just that now I treat alpha as some summary that could be an average, that could be, there's some mapping that describes which, you know, states or elements that I'm grouping here, but it's basically just a grouping. Even more broadly, we just can refer to it as a dimension reduction, right? I have two dimensions, I've got A and B, and now I'm gonna just call both A and B alpha, and that means that I now have one dimension, right? So I have just alpha. Again, these sort of could be anything, but the notion is just that when I'm talking about dimension reductions and macro scales, I'm talking about something this simple. I'm talking about very, very simple stuff. So we can sketch this out a little bit more. Both of these causal models, we can refer to them broadly as causal models, are of, let's say, the exact same system. But you know, on the right, we've replaced A and B with a new element, alpha, and that represents, in some dimension-reduced way, the joint state of A and B. So to actually do this mathematically, you have to specify how alpha represents A and B. So let's say that alpha is a binary element, right? So it could be either 0 or 1. And let's say that A and B are also binary elements, so they could be 0 or 1. But the difference is that if alpha is in state 0, like alpha equals 0, that is true if A and B in their joint state are either 0, 0, 0, 1, or 1, 0. And alpha is in state 1, alpha equals 1, only if A and B both equal 1, right? So in other words, if we're like looking at this system at two different spatial scales. And at the macro scale, we could say alpha equals 0. But at the micro scale, we might say AB equals 0, 1. And that would be the same system, but just re-described at a macro scale versus its micro scale. So notably, macro scales are dimension reductions. So they throw out information. So what is lost at the macro scale is the difference between states like AB equals 0, 1 and AB equals 0, 0, right? If I just told you that alpha equals 0, you wouldn't know exactly which microstate I'm now referring to. You wouldn't know the underlying microstate. You would know some information about the underlying microstate because you know that it can't be the case that A and B both equal 1, because otherwise alpha would be 1. And notably, that's an example of multiple realizability. This is another term from analytic philosophy that I found useful in explaining these things. So if at the macro scale, the system is alpha equals 0, this could mean that A and B are in any of 3 different possible states. They could be 0, 0, they could be 0, 1, they could be 1, 0. Just like how, given some temperature in a room, the particles could be in many different configurations. So first, there's just a couple things to note before we move on. Nothing is actually changing at the macro scale. Right? So the only thing that's changing is the scale at which you as a modeler are describing the system at, right? So there's no extra properties, nothing has been added in at the macro scale. You're just re-describing the exact same system that you had, but in a dimension-reduced way. And also note, there are all sorts of possible ways to do dimension reduction on a system. So there's an astoundingly large, I think I calculated it out once, it was like a Bell number, for the number of possible macro scales given like just a binary causal model. So we could have reduced AB in a number of different ways in the previous figure. And then it's also worth to note that although we're talking, all the examples I'm going to show are from extremely simple systems, there is no reason that these techniques or ideas are constrained to such simple systems. So you could have a system that is very complex. Oops, go back. You could have a system that is very complex, like this system on the left here, which is alpha, beta, gamma, and it has a bunch of different microscale elements and interactions, and you could summarize all of those. Right. And now you could represent it in a big dimension reduction. Now there's 3, elements up at the macro scale. So this is why I like talking about simple systems, is that we can show very particular cases of causal emergence in simple systems. And then we can apply those techniques to very large systems as long as we can represent them in the same way. Okay, so this is what I just described was the way that we're going to talk about higher level scales, macro scales and micro scales. But there's also this important term, causal emergence, right? And why is causation important, just broadly? Because if you're not talking about causation, it's unclear why the emergence matters. You can say something is emergent, but so what? Because something needs to have causation in order to matter or make a difference, which is literally one of the things that causation means in the world. So we don't want to know, are macro scales sort of present, or can you model the system at a macro scale, or so on? That's very obvious. The answer is yes. What's more interesting is, does the macro scale add anything in terms of causation that the micro scale does not, and thus causal emergence? And the way that I prefer to formalize emergence, and I think is probably the best and broadest way, is to draw on some of the work of Judea Pearl, who's a wonderful mathematician and who's been working on formalizing the notions of emergence, formalizing notions of causation. And we don't need to use everything in his work, which is actually quite complicated, but we can just use some very simple ideas that are broad. And an example of this would be to understand causation in a system. You want to approach it as if you are doing interventions on that system, and you can represent those interventions mathematically using something he calls a do operator. So as a very simple example, let's say you buy a new house and you don't know what all the light switches in the house do yet. So what everyone does very naturally is they go around and they apply the do operator to the light switches. So they go around and they turn the light switches up and down to see if it, say, turns a light on and off. And once you realize that I can do light switch up and then the light comes on, you say, aha, this is the light switch that's connected to that light bulb, meaning that I've found a causal relationship. This broadly, this notion of a do operator and then looking for some difference following the application of a do operator is sometimes called an intervention-based account of causation. Sometimes it's called the difference-making account, since flipping the light switch made a difference to the state of the light bulb. It doesn't really matter what exactly you call this. The point is that you're interfering with the system, and that's how you are approaching understanding the causation of the system. And of course, interventions capture something that mere correlations cannot. So two different switches might be really highly correlated, right? So or a light switch and a light bulb might be highly correlated. Like, for example, a porch light and a lawn light. Generally, if the porch light's on, the lawn light will be on. Or generally, if the porch light switch is up, then the lawn light will be on. Maybe you always flip both up at the exact same time, right? But you can tell that they are independent causal relationships, and that there's actually two switches and two bulbs once you start intervening on one and then the other, right? Because I can do up just one of them and see if that makes a change. So this is very important because this distinguishes talking about mere correlations from talking about causation, is using an intervention-based approach. Okay, so let's go back to our simple causal models. What would applying the intervention-based notion of causation look like for our simple causal models? So we can think of it as doing a surgery. This is also Pearl's terms, where we fix the state of a variable and then see what happens. Generally, we start with some causal model in a state, and we're going to use like a very simple one that hopefully a lot of people are familiar with. So this is just an AND gate. An AND gate takes two inputs, and it makes a decision about the next state. So it outputs a particular state, and it does so according to a truth table. And the way that this is represented right now is that, of course, the inputs are broadcast to the AND at some particular time step. So we can, again, just make everything as simple as possible. We'll discretize time. So at time t, which is some time point, we have a equals 0 and b equals 1. Those are the inputs to the AND. And hilariously, this is actually incorrect. I'm not sure why, but this AND should be 0, because if you look at the truth table, if it's getting 0, 1, it should output 0. So if for some reason you did see this, you would know it's actually not an AND gate. Let's move on because I think the next one's. Okay, so in order to know if A is a cause of the AND, we can hypothetically flip the state of A to see what happens. And we can do that, and we can state that as do A equals 1. So let's say that we had previously, right, we had A equals 0 and B equals 1, right? The AND was then off, although the figure was wrong. The AND was then off. So now we can instead do A equals 1, which means that we perform a surgery on our model and we say, no, let's set the state of A to 1 automatically. Then what happens? Well, instead of the AND being off or 0, the AND would be 1 following this intervention, meaning that we performed a do operator. We saw that performing the do operator made a difference to the future state of the AND. And this indicates that there is causal influence from A to the AND. So assuming that you actually have, one thing I really left out here is how do you get a causal model in the first place, right? So there's all sorts of ways to build causal models. And I actually think there's no like one perfect right way to build a causal model. You can build a causal model in all sorts of different ways. As I said, we all sort of, when you buy a new house, you build a causal model of the house and the relationship of the light switches to light bulbs, because you go around and you apply the do operator enough, and eventually you realize how everything works. And there's all sorts of much more fancy ways of creating causal models. But let's just leave that aside. Let's just assume that you have a very good causal model. And again, by causal model, I mean just what we've been looking at, sets of variables that have influence on each other. And assuming that you could also calculate the effects and the outcomes of interventions, this represents, according to Judea Pearl, a deep understanding. So this is now Judea Pearl. He writes, deep understanding means knowing not merely how things behaved yesterday, but also how things will behave under new hypothetical circumstances. Interestingly, when we have such an understanding, we feel in control, even if we have no practical way to control celestial motion, and still the theory of gravity gives us a feeling of understanding and control because it provides a blueprint for hypothetical control. We can now see how this model of interventions leads to a formal definition of causation. Y is a cause of Z if we can change Z by manipulating Y. Namely, if after surgically removing the equation for Y, the solution for Z will depend on the new value we substitute for Y. So just to put that in plainer language, if manipulating a variable Y entails a change in some other variable Z, then this relationship means that the Y has some degree of causal influence on Z, provided you are doing things like also making sure that other variables aren't interfering and so on. And this is just as was just shown in terms of the A causing the AND's future state to change. Okay, so let's apply some understandings of, let's put all this together. And of course, what we're going to show is that there is instances of macro scale causation. And so macro scale causation means that you should attribute the deep understanding of causation to the macro scale relationships rather than the underlying micro scale relationships, or at the very least, that the macro scale relationships add something and seem to contain something that the micro scale relationships do not. And how exactly one goes to show this, you can do it in all sorts of different ways. But one of my favorites now is to go back in history and to look at some of the very earliest definitions of causation and see if we can find instances of causal emergence using those examples. So let's consider David Hume's definition of causation back from 1748. And it's considered, as laying the groundwork for almost all further thinking about causation. So Hume gives two different definitions of causation, actually, technically, although the first is more commonly attributed to him because Hume develops it a lot. And he says, we may define a cause to be an object followed by another, and where all the objects similar to the first are followed by objects similar to the second. So this is sometimes referred to as the regularity account of causation. If two things are paired with one another and correlated with one another enough, say burned toast and toaster ovens, then we eventually say that one is the cause of the other. Now, as we've seen from Pearl's work and others, that's not actually a very good definition of causation. So I'm not saying to use this definition of causation. My point is that even with this very primitive definition of causation, we're going to see a simple example of causal emergence. Okay, so we can just directly apply Hume's regularity account of causation by looking at the pairings between states. So let's consider this particular system where there's a little bit of noise in the relationships. And if you look on the left here, you see that there's a 3-node system, A, B, C, and A transmits its output to B and C, and B and C both respond via a truth table, right? So this truth table says A, that says, in the input A, and then the output is whether or not it's on or off. So for example, if B receives an input from A, that's 0, then the chance of B now becoming 0 itself, the chance of B equals 0 is 0.3. Right? If B receives a chance, so that means that it might flip, right? So it might be that A gives B a 0 and B now actually outputs a 1, right? So there's some noise in the system. And C works the exact same way. Okay, so we can think about this now as Hume's regularity account. So if we see, let's look at the pairings. If we see A equals 0, and both B and C now only have an independent 70% chance of being 0 given the output, we might see A and B and assume some state. So for example, if A is 0, the highest probability is that you do see 2 zeros, which means that it's strongly associated with that. But that only occurs a small percentage of the time. So point being is that at the micro scale, the states don't regularly follow other states. Okay. Now, at the macro scale, we take the exact same system and we group over these elements. Now, when we do that, you'll notice that the chance of both elements now being 0, 0 is pretty low, right? Even if A is 0, the chance of both elements being, I think I actually reversed this output. So this is the output, I think, of it being 1, not being 0. So no wonder I was like, wait a minute, so I'm describing this wrong somehow. So no, the output is flipped from what I was talking about. I should have labeled that better. The output is the chance of the output being 1. So it has a 70% chance of being 0 should it receive 0, right? Which is still higher than 50-50, but still pretty low. So now, though, if you group over both of them, the chance of both of them being 0, 0 is actually quite high. You only have a 0.09 chance of the bit flipping at the macro scale. So what that means is that just from a regularity perspective, the relationship between A and B is irregular, right? The relationship between A and C is irregular. Even the relationship between the joint states, it could be one of any 4 states, right? So it's going to be quite irregular, right? Because it'll be A's one state to one of B or C's 4 possible states that it could output to. But meanwhile, at the macro scale, the relationship between A and alpha, which is just a dimension reduction of the exact same kind that we looked at before for 2 nodes, right? Where 0, 0, 0, where 0, 0, 0, 1, and 1, 0 all map into 0, and 1, 1 maps into 1. The relationship is perfectly regular, almost perfectly regular. So, okay, so that means that systems are regular at macro scales and irregular at micro scales. So now, I don't think that this is a great case of causal emergence because I don't think the regularity account from Hume is a great measure of causation. But it goes to show how unavoidable causal emergence actually is. Even if you choose a very simple, maybe the oldest, sort of more mathematical account, you could argue over, Aristotle having some preference regarding, theories of causation. But I think Hume is credited as being one of the, first modern sort of accounts. Even if you go back to that, you can find instances of causal emergence, provided you're using the regularity count as a measure, because just think about it. Macro states are better correlated with each other than microstates because microstates are noisy. So again, according to Hume's definition, this is like a good example of causal emergence. So let's move on to another example that's maybe a bit more modern, right? So again, this is going to draw from analytic philosophy. So this is David Lewis, and writing, more than 200 years later, he defines Hume's second account of causation that he gives, that Hume doesn't spend much time on, but he does give a counterfactual definition. And David Lewis defines it in this way: something is a cause C of some event E if, given that events C and E took place, and then C had not occurred, E would also not have occurred, right? So again, we'll just go back to really sort of simple, boring examples. If I had not flipped the light switch, the light would not have turned on, right? So this is a nice counterfactual definition of causation. So let's just take the counterfactual definition of causation, which is also very primitive. You might say, you could complexify it. You might say, again, it's not a perfect measure of causation, but it is a very famous measure of causation. So let's see if we can find an example of causal emergence where it seems as if the macro scale is actually adding something that the micro scale doesn't possess. And also using this Lewis definition of causation, it's quite easy to find an example of causal emergence. So here's a causal model set up a bit differently. This time, we're going to get rid of the noise, and add in just redundancy instead, which means we can just use the same sort of AND system that we've been talking about, where A and B input to an AND. So again, we can consider this system in a macro scale. Let's use the exact same grouping, wherein inputs A and B are grouped into alpha, such that 0, 0, 0, 1, and 1, 0 are all considered alpha equals 0, while 1, 1 is considered alpha equals 1. So if we saw, for example, alpha equals 0, then we don't know if it could be that A is 0, or it could be that A is 1 and B is 0. We don't actually know. It could be one of any three states. And interestingly enough, this actually, viewing the system at this scale changes what you assign this, what you think of the system as. So at the micro scale, this looks like an AND gate, and it is an AND gate. But at the macro scale, you could say that this is actually a copy gate, because it's copying the binary state of the macro scale, which is either 0 or 1, and the copy gate is also either 0 or 1. And you can just think about this as, if you look at this truth table over here on the left, where A, B are inputting to AND, then you can just think of this as, well, we've grouped all these states together. We've grouped 0, 0, 0, 1, and 1, 0 all together. They all equal 0. Well, if you do that, then you end up with a copy gate. Right. Okay, well, let's apply this very basic but fundamental counterfactual definition of causation that that Hume and then Lewis gives us. So to compare the two scales, we want to know, does the AND counterfactually depend on its inputs, right? And if so, to what degree it counterfactually depends. So we can apply the do operator again in exactly the same way. So we can do, instead of A equals 0 and B equals 0 and then of course equals 0, we do A equals 1. Right? So we perform an operation. And what we see is that that makes no difference to the system. A and B were both 0. So if I flip one of the states, then the AND is still going to be 0. You would have to flip both of them for it to be 0. But so if I do an intervention and I change the state of A, I see that, well, it doesn't actually depend on the state of A. Now you could say, well, I changed the state of both at the same time, but what do you change it to, right? You could change it to 1, 0 or something, right? You could assign the joint state as some different joint state, and it would still not matter to the system. But at the macro scale, you cannot change the state of the input without changing the state of the output. That is, there is counterfactual dependency. So remember, alpha was 0 and the copy was outputting 0. But now if I do alpha equals 1, then the copy gate outputs 1. So the result is that there's counterfactual dependency at the macro scale, but not at the micro scale, or at least not for most interventions. Which means that the AND is just not counterfactually dependent on on the state AB equals 0, 0, because I can change that state in a couple of different ways, and it has no input on the output. But at the macro scale, it is dependent. So we can get more complex with examples like these. So this example is, and I won't go through it in detail, but this example is something that was used in our first paper about causal emergence, using a much more complex measure of causation. So, right, because broadly, right, we should think about measures of causation. Just to go back 1 second, we should think about measures of causation as like a broad family of related measures, and I'll talk about this in a second. But you can have very simple measures of causation, and you can have very complex measures of causation. So in in this model, which we published back in the first paper about causal emergence in 2013, that was using the effective information. And the effective information uses techniques from information theory to capture the degree of causal influence using bits. So it can say, the relationship between A and C is worth, 1 bit. The relationship between, A and D is worth 2 bits or whatever. And even in these, this quite complex and a very, very modern definition of causation, we still found examples of causal emergence. Here, there's sort of 1.15 bits of effective information at the microscale, but 1.55 bits at the macroscale. So we sort of generated 0.4 bits of causation just by moving up to a macro scale. Now, when we originally proposed this, we were working solely with the effective information. And one of the criticisms of our work, and I think that, when anyone says that they have a mathematical theory of emergence, one should be very critical of it because it's a really big claim, especially if you can show it in simple examples, right? Now, one of the criticisms was that, well, maybe there's something particular about the effective information, right? Like the effective information is a relatively complex measure. It is sort of a variant of the mutual information, but it's actually not the mutual information due to assumptions around sort of the input distribution. So you could say, well, maybe causal emergence, this finding that you can sort of generate these extra bits of causation up at the macro scale. Maybe that's just because this measure is even though it seems good from a first principles perspective, maybe it's just sort of wonky. Maybe it has some sort of weird or unnatural aspect to it, and that is what's causing this, right? So in other words, maybe you just don't have a good measure of causation, and that's very hard to address because there probably is no one absolutely perfect, agreed upon by everyone measure of causation. Causation is sort of this this broad family, and the way that I think about it, and I think it's the best way to think about it, is that causation is a lot like complexity. So if you look at complexity theory and you look at complexity science, there is no one perfect mathematical definition of complexity that everyone agrees on. Instead, you have sort of a family of measures which are related, right? So you might say the Kolmogorov complexity, right, would be a great example of that. But you could also say the mutual information to a degree a measure of complexity. You could also say logical depth is a measure of complexity. And so there's sort of this mathematical family of measures. And we all know that there's a very big difference between very simple systems, which all the measures of complexity will return, 0, 4, or low values for, and like very complex systems, like a really complex cellular automaton or something. And then all the measures of complexity should return relatively high. But no one has any no one has sort of boiled it down to saying that there's absolutely exactly one definition of complexity and then everyone has to agree on it. And so when talking about causal emergence, the difficulty is always that, well, it's causal emergence, so we have to choose a measure of complexity, and it would be bad, and it would indicate that maybe causal emergence isn't real if causal emergence was totally dependent on one highly particular measure of causation. So if you could only measure causation in one way, that showed causal emergence, and all the other ways of measuring causation, you don't see any causal emergence. Now, as you just showed, that's almost certainly not going to be true, because even if we go back and we take very simple, older historical measures of causation, we can still find examples of macro scale causation, like in Hume's regularity count, where macro scales are more regular with one another, or the counterfactual definition, where macro scales of systems can be more dependent on one another than any of the underlying micro scales. So we already sort of know that that's not true. And why is that? Is because measures of causation are generally mathematically pretty similar. Again, just like the analogy to a family of measures of complexity. We first sort of took this approach with myself and Renzo Comolati at the University of Milan, and we just measured every measure of causation that we could sort of get our hands on and formalize for simple systems. So some notions of causation are very high level, and you can't really formalize them very well. But there are a bunch that you can just go out and apply directly in very simple systems like Boolean networks and Markov chains. And when you do it, you find that causal emergence crops up pretty much everywhere under some circumstances. So that is taking the same system, modeling it at a macro scale versus the micro scale. You find, either the macro scale fits the definition of causation and the micro scale doesn't, or if it's a degree of causation, the macro scale has more influence than the exact same things occurring at the micro scale. So I won't go directly into all these results because it would require going through all the different measures of causation that we looked at. But very broadly, we should think about it as, so here the green is the degree of causal emergence. And then this is us varying the parameters of the model in all sorts of different ways, and assuming all sorts of different types of interventions and how we're doing the interventions and so on, right? So again, this is sort of being as agnostic as possible. And the ones in which it's all purple, by the way, are not measures of causation. So they're the opposite. So that's degeneracy. So exclude that one from the screen. So as you can see, you basically can find causal emergence pretty much anywhere in terms of what measure of causation you take, or at least I should say you can find instances of macro scale causation that outweigh the underlying micro scale. So I just want to give some definitions before moving on to talk about what we can do with this analysis. So first, when I say macro scale causation, what I always mean is that the macro beats the micro scale. That is, there is macro scale causation that the micro scale lacks, and we do that by going out and literally applying a measure of causal influence at the micro scale and at the macro scale for the exact same events. Again, I think that that's really key for people to understand. It's the exact same events. It's just being redescribed, and you find more, or you find that the macro scale fits, because it could be binary, right? It could be 0 or 1. It's either a cause or it's not. You find that the macro scale is cause and the micro scale is not cause. So what can you do with the theory of emergence, right? Well, you can find natural scales of description. So what is a natural scale of description? Natural scale of description would be like if you could describe, your laptop at all sorts of different spatial temporal scales, right? You could take the various microchips and like average them together into some really wonky or strange causal model, and that causal model would be terrible. It wouldn't be a natural scale of description. But if you looked at, say, like maybe the machine code, you get like this really natural scale of description. And we all know that there's these natural, or we all basically operate under the assumption that we can talk about systems in terms of their natural scales. And indeed, that's one of the things that science does. It likes to find a very good sort of natural scale of description, like describing biology in terms of cells. And then it focuses in on that and creates a scientific discipline around that particular scale. We can now give a precise mathematical definition of a natural scale description, again, assuming some particular measure, which I'm saying, we can remain agnostic as to what the measure of causation that you're using. But a natural scale description is when some particular scale contains a large degree of macro scale causation relative to the degree of dimension reduction. So you've thrown out some information and you've maximized the amount of macro scale causation that you found. So let me give an example of this. If we just imagine some system, it could be anything. It could be a brain, it could be a biological system, it could be one of these very simple like Boolean networks that we've been talking about. And you imagine moving up the spatial temporal scale, which would be moving along the x-axis here of increasing amounts of dimension reduction, right? Because the more dimension reduction you do, the more of a macro scale it is from the micro scale. The more dimensions you're shaving off. Like imagine going to a system, going to its mathematical representation, and you're just shaving off dimensions. of your mathematical representation of the system. And on the y-axis is the amount of macro scale causation, the amount of causal influence you're finding at macro scales that you're not finding at micro scales. And now what you can do is that you notice that, at first, the first star here is that you've shaved off just a little bit of causation. You just shaved off a little bit of dimension reduction. And you haven't had too much of a gain in terms of the amount of macro scale causation. But in terms of the next star, right, it's that you've only shaved off a little bit of the dimensionality of your system, and you've sort of hit the jackpot in that you've got this huge increase in the amount of macro scale causation that you're seeing, right? And by balancing the two, by finding a maxima of the two, right, which then that is a natural scale of description. So now, notably, for some measures of causation, they're doing this automatically. So this is what we didn't realize. This is basically what's missing from the first paper, which we didn't realize. So the effective information can be, we knew that it could be broken down into two terms, the effectiveness and the size, and that those two things work together. You can decompose the final value of the effective information into those two terms. The size value is always increasing when you go down to the micro scale, and it's decreasing up to the macro scale because, of course, you have less options, right? Because remember, the effective information is an information theoretic measure of causation. So, it's all about the number of states that a particular state rules out, and so on. So, what it's implicitly doing is searching for the system where you have the maximum change in the effectiveness. And again, that's a particular mathematical term, but it means something very similar to like counterfactual dependency or degree of noise in the relationships. So you're searching for the maximum of effectiveness while you have the minimum loss in size. So some measures of causation already implicitly do this, and therefore, to find a natural scale of description, you just maximize that measure. So that's how the effective information works. But that made it look like maybe our results were like very dependent on the effective information. But actually, causal emergence exists across, essentially, as far as I can tell, every measure of causation I've looked at that is sort of the interventional difference-making account. There might be very different notions of causation that it doesn't apply to, but those notions of causations aren't really used in science. They're like very, very philosophical. Things like like Aristotle's different notions of causation, or things like that. That just like they don't really seem like the sort of modern theories of causation that we can apply to like a causal model. So when it comes to those, as far as I know, causal emergence can exist given some particular system architecture in all of them. And to then find a natural scale of description, what you do is that you take your measure of causation and you look for the greatest gain that you're getting in terms of the macro scale causation for the minimum amount of dimension reduction, right? Because you always, I think it's very natural in modeling systems that you want as many dimensions as possible. As we said, it seems like compression is sort of innately bad. So the question is, what are you getting for your compression? Okay, so then when you do that, just to give an intuition of this sort of notion of a trade-off, we can go back to the effective information, and we can see where it peaks when you start varying network parameters. So this was a paper from a couple of years ago where we looked at what happens when networks break from being scale-free. And what we found was that the effective information, the amount of causal emergence is 0 until you hit the degree at which a network is mathematically scale-free. So people talk about scale-free networks. So scale-free networks are the very beginnings of where it looks like you might begin to get causal emergence. And then once you get into past the scale-free regime, then you get a lot of causal emergence, and then it goes down again as you coarse grain. You basically are shaving off too many dimensions. And just to give you a like a visual intuition of what that looks like. If you look at the bottom here, this is the x-axis here. So this is what we're varying in terms of the network structure. So you start off on the left here, and you're varying the degree of attachment between the elements of the system, and you don't see any causal emergence because everything is sort of one-to-one. There's no like joint groups. There's nothing to sort of average over. Then you start to vary it such that you begin to see some groups form, right? The peak of causal emergence will be, somewhere around this middle one where you have some distinct groups. You still have individual elements, but you have some distinct groups. But then you can actually coarse grain too much and you shave off too many dimensions and you end up with like a binary system where all the nodes on the outside are grouped into one node and all the nodes on the inside are grouped into one node. And it's just not very interesting. So it's not a natural sort of scale description. And you can apply the causal emergence framework to all sorts of things. So we've done, a good amount of empirical work. I think we could do way more, but just to sort of give an example of what one can do with this, we looked at the protein interactomes and measured the degree and the change in effectiveness and other like quantities related to causal emergence, and what we actually found was that there was an increase in eukaryotes compared to like as evolution went on. So I think that like this is sort of it's fun research because we're using like really big data sets across like thousands of different species. I don't know to what degree like I really want to rely on it as a direct proof of anything, because this is from like protein interactomes that people have assembled. We never know how accurate those are. There might be all sorts of other stuff in the causal model, but I think it's quite interesting and suggestive. And that some other examples is that if you measure the degree of causal emergence, you find a lot more of it in biological networks than you do in technological networks. So biological networks seem really sort of naturally to gravitate towards macro scales. That's probably because, and we've done some other research on this, if you build your system up at a macro scale, it's more robust to error. In fact, that's basically exactly what causal emergence is saying, right? Is that macro scales, as we said, right? Macro scales are more regular, macro scales are more robust. So if my causal relationships are between my macro scale elements, I can lose a micro scale element and I'll be okay. The system will keep working. So, there might be ways to design like robust to attack networks and things like that using the causal emergence framework. And if you want to check out any of the relevant citations, I've put them here, so freeze the screen and you can sort of go through them historically. But what I am excited and hopefully will one day get to share is this upcoming book on causal emergence, The World Behind the World. And again, that's coming out July 25th here in America. So with that very sort of high level overview of how I'm thinking about it, I'll end it and take questions here. And thank you so much. I know how late it is there, and I really appreciate everyone staying up to listen to this. So thank you.
Okay, so first of all, thank you so much.
Again, a little bit of emergence. Right here.
Feedback again.
Yeah, I'm so sorry about that. So first of all, I would like to thank you so much for the amazing talk. So you mentioned your new book, and we are able to translate it, and we are happy to translate that, and we will contact you soon. And for the earlier, we have reached out from the Swarma Club. So you wrote a book named The Revelations. And for that book, we have almost finished the translation, and we will send you the email for ask for the permission. And for the new book, we are happy to translate it. And I think Professor Erik Hoel gave a very exciting talk from a very interesting question. So how did science get its skills? So Professor Erik Hoel gave us a roadmap from the automatic physics to psychology and economics. And for the amazing paper, causal emergence is widespread across measures of causation. Erik give us different measures of the causation, and he said that the measures of causation are mathematically highly similar, which is a sentence that I like pretty much. And now we have Professor Zhang is on site, and I noticed that Professor George from Captain, so who is online as well. And I hope that maybe we can have a chat. And I would like to ask, is there any questions about the Professor Erik Hoel's talk?
Hi, all right. Nice to meet you again. See you again. Okay, so thanks for your talk. And I have a question about the dual operator. Is the intervention. So I think I remember that you give us an example that there is a conflict between the macro level intervention and the macro level intervention. Is that right?
Not so much a conflict as it would be that you can, if you apply the do operator to the microscale, the result is that the microscale fails the counterfactual definition of causation. So it says the microscale was not a cause. But if you apply the same measure up at the macroscale of the same events, the measure tells you that the macroscale is a cause. And this, normally, a lot of the more complex measures of causation they come in degrees. So you might say the macro scale is more of a cause, but in these very more basic definitions, like counterfactual definitions, things either are causes or aren't, right? It's just, it is or it isn't. And in this case, the microscale isn't, because if I change the state of the microscale, I don't see any change at all. And if I change the state of the macro scale, I do see a change in the output. And so it fits the counterfactual definition of the macro scale, of the counterfactual definition up at the macro scale, but not at the micro scale. But the same things are happening in both cases, right? So you apply the measure concerning the same relationship in the same model, but it's just that the micro scale, you get a 0 back, and at the macro scale you get at the micro scale you get a no back, and at the micro scale you get a yes back in terms of the definition of causation.
Okay, so thank you. A following question is how can we do intervention on the macro level? Sometimes, of course, we can understand as a kind of to decompose the states of the macro level into the lower levels. However, I think maybe can we just really intervene the higher level states? I'm not so sure.
Yeah. So no, you're absolutely right. When you are doing like a macro scale intervention, something is changing about the micro scale, right? Mm-hmm. You're just changing it so it's different, right? So you can't just intervene on you can't intervene on a macro scale and have no changes at the micro scale. The micro scale will change when you're intervening on the macro scale, because the macro and the micro are the same thing, just at different levels of description.
Yes.
But it's just that the macro scale, because again, I think it's very subtle, but there's a difference between the original question is, does the state of the macro satisfy the definition of causation given what occurred? And then we do the analysis, which means flipping it to the counterfactual state, And And then when you do that exact same principles, exact same reasoning, starting from the exact same state at the micro scale, you get a different answer, right? And that's because the question is not, in our counterfactual analysis, are we looking at all the same states? The question is, we start with the same states, but then what counts as, like, so for example, at the micro scale, if I say, I want to apply the counterfactual definition of causation. So I say, not alpha equals 0. Because remember, so this is what we start with over on this slide. We start with alpha equals 0, copy equals 0, right? That's the relationship we're looking at. And we want to know, does copy equals 0 counterfactually depend on alpha equals 0? And that's the same as alpha equals 0, A equals 0, B equals 0, and equals 0. Does that and stated and counterfactually depend on A and B? And then, so we start with the same state, same transition of states, right? One is just a redescription of the other. But now we're going to apply the counterfactual definition. So we're going to ask, okay, but if I had done something different, so if I had done not the input, right? So here we say, well, if I had done not A equals 0, that means that I had to have done A equals 1, and that does not change the output. But at alpha equals 0, if I say, well, if I had not done alpha equals 0, I would have had to have done alpha equals 1. And if I had done alpha equals 1, then I would have the copy be output to B1. And that's different than at the microstate. So there is a difference of what occurs, but not in the actual, there is a difference of what occurs in the counterfactual analysis, because you're asking the question at a different scale. But there's no difference in what physically occurred. Like what actually occurred was you had 0, 0, and then the and output is 0. And then in this case, you had alpha equals 0 and the copy gates output 0. And then when you apply the counterfactual analysis at each scale, in one case, it doesn't satisfy it at the micro scale. And in the other case, at the macro scale, it does satisfy it. But it's not that we're just applying like the do operator to the macro scale and somehow the micro scale is unchanging. When you apply it at the macro scale, there is something going on at the micro scale, which is that now both A and B are being set to be 1, 1. And that is different, but this is all a hypothetical, right? Because remember, the only thing that actually happened was the exact same thing in both cases, right? So, yeah. So like, right? So it's like, well, yeah, there is a difference, right, between the events, but they're hypothetical events that we're using to determine if these original events are causes or not. So it is very subtle, but actually in both cases, the exact same thing happens. It's just that your counterfactual dependencies look different depending on what scale you're at. And you can find a scale such that it's like very counterfactually dependent.
Yeah, I think this point is very interesting because when we consider controls, actually, just because a one macro level state may have the many number of macro level states. So that means if we control the macro level, then macro level, sorry, the higher level, actually we have a kind of fuzzy control on the lower level. Can I understand this one?
Yeah, no, absolutely. If you intervene on the macro, you definitely have less knowledge of what's going on at the micro, but you're still controlling it, right? You're still like a macro scale intervention is still controlling the micro scale. So for example, but it might be a bit of a fuzzy control, exactly as you said. So if instead, an example of this would be if instead I had do alpha equals 0, right? Like if instead it had started as alpha equals 1 and I wanted to check the counterfactual, so I did alpha equals 0, there's this question of, well, what microstate do I place it in? And I think the answer is you place it in some sort of distribution. So you say, well, it could have been 0, 0, it could have been 0, 1, it could have been 1, 0. Now here is not going to matter because they're all going to give the same probability output, but it could matter in that there could be subtle differences in the probabilities or something like that. And so, yeah, it would give you a form of fuzzy control.
Yeah, I think it's interesting. Yeah, thank you.
Okay, so are there any questions from the online or on-site audience?
Hi, Professor Hoel. Can you hear me?
Yes, I can hear you.
Yeah, I have a question about another paper of you called causal geometry. I found that that is a very interesting paper, and including quite some stuffs that's hard to read for me. And but I've also found that there are fewer cited for that paper. So because that's work a few years ago. So from the point of view for the time being, do you have any update on that topic?
It's a great question. So that paper very broadly was about trying to take these techniques and apply them in continuous systems. You'll notice that everything I've talked about has been discrete. So I've been talking about very simple logic gates and Boolean networks. Now, that's not as much of a limitation as you might think, because so many models, causal models in science, fit that description. So an example might be like a gene regulatory network, right? People make discretized models of those all the time. Another example might be like a neural network or something like that, where it's fire or not fire, right? There's sort of all sorts of models that you can make that are discrete, and all the math is much simpler in discrete systems. And so again, I prefer to work with the simplest thing possible, because that way, if I'm making a claim that there's actually macro scale causation occurring, right, then you can sort of prove it, more easily. But we've always wanted to expand these ideas into talking about continuous systems. And what I and my co-author saw was that there's this field of information geometry, and it seems as if there's some natural connections between the two. Now, information geometry is a very complex, and difficult to understand field. So we tried to apply some of the same principles, but talking about causation instead of information, and arrive at sort of similar conclusions of, yes, you can shave off the continuous dimensions of systems, and you see some sort of gain in what is essentially like the derivative between two variables, like how much one variable depends on one another, like at an instantaneous point in time. But while I really like that paper, I think that sometimes it's like we're combining too many complex things at once, right? We're trying to take something that's already an idea that is subtle and difficult to grasp in very simple systems, and then applying it to very complex systems, and even then they aren't that complex, they're just continuous, which already makes them harder so to work with and talk about. So I don't have any major updates, because I think that there's so much data in the sciences that is discrete and fits these types of causal models. And also Pearl and other people who talk about causation mainly talk about these sort of causal models like DAGs and these other entities, and they don't talk as much about continuous variables. But I think that like in the long run, there needs to be like a continuous version of the mathematics, and that was our first attempt at that. So yeah, I think it probably did get less citations, because I think it's just far harder to understand, and that's like both on us as sort of maybe failing to explain it well, but also maybe just that it's sort of combining, causal emergence, which is already sort of complex and draws, yes, a lot on math, but also some philosophy and causation and, all these other things that normally aren't sort of all put together. And then also put that into, continuous systems and information geometry and other stuff that's also very difficult. So, I would love to sort of do more on the continuous side of things, but I honestly don't have any major updates on that. Other than that, I think that these techniques can work in continuous systems. I mean, you could think of that paper as basically a very simple proof of concept of just like, can we talk about causal emergence in continuous systems? And then the answer is, well, yeah, it looks like maybe probably yes.
Thank you, Professor Hoel. That's really a great work. And I think it has been underestimated. Thank you.
Okay, so for the last question, we have a question from the on-site audience, and I will pass the microphone to him.
Okay. Hello, Eric. Nice to see you again. Yeah. I'm not sure if I get this correctly. When you were talking about supervening, you mentioned that the macro state supervenes on the micro state. You agree on that, right?
Mm-hmm.
Okay, that's one thing. The other thing, is there any unique property that only exists in the macro level that cannot be reduced to the micro level, cannot be explained by the micro level? You said no, right? You said yes, right? There is something unique on the macro level. That's your opinion, right?
Yeah.
So how could that be? Like on one hand, it's supervening, on the other hand, there's something unique you cannot reduce.
Great question. And the answer is very simple. In fact, it's so simple that I think that most of the people who have, again, emergence has traditionally been looked at mostly by philosophers, right? So I think that most of them, except a couple philosophers have noted this, but they never really expanded on it. So there is one property that macroscales possess that no microscale can ever possess, and it doesn't violate supervenience, which is that macroscales are multiply realizable. You can have the same macroscale with different underlying microscales. So an example would be temperature in a room, right? You could have the same temperature in a room, but the particles could be in all sorts of different configurations. And in fact, that's the definition of the macroscale, right? And that is a property that no underlying microscale can have. And the multiple realizability is ultimately the reason why macroscale causation can exist at all. Because once you introduce this multiple realizability, if you just think about it very broadly, imagine that you have a system and there's noise in it. Forget how or why, right? There's just some noise in it, right? As I coarse grain, right, the noise will decrease because my states become more multiply realizable. So the relationships between the states will decrease in terms of the noise. And that's fundamentally where this extra causation is coming from. It's coming from the multiple realizability of the macro states. So, but there's no like magic or like extra stuff. I think people really sort of want there to be, right? It's just that. But people hadn't really thought about the relationship between multiple realizability and the actual measures of causation, and between multiple realizability and how it decreases the noise and allows for more regular and deterministic states, and how that ends up affecting the macro scale causation.
Okay, that is an excellent explanation. Do you think the sloppiness of a model variables plays a role in raising up causal emergence?
Yeah, so that's such a good question. I can't say I know 100% for sure, but I think yes. So I think that what the research that you're referencing is picking up on some of the same ideas, but is approaching it purely from information theory. And I think that that's fine. I'm not saying that that's wrong or anything, but because it doesn't incorporate causation, I think there's sort of this, like, yes, it's nice for a modeler, right? But it's not really saying that the macro scale is doing anything extra. I think causal emergence sort of goes by looking at measures of causation, goes a bit above and beyond. But you could think about it as you could probably, and again I say probably because the only sort of continuous stuff is this causal geometry paper, and we didn't get all the way into sloppiness at that point. But you could probably say something like, if you took sloppiness and you applied it to causation rather than information, what you would notice is this significant increase in your measures of causation as you sort of built more sloppy or fuzzy models. And that would be causal emergence. Now, again, I don't know if the mathematics of that work out perfectly because I haven't done it. But my guess would be that they're actually doing something quite similar, but they're just looking purely at information theory and they're not really looking at causation. And while there are some like links between the two, they're also, somewhat different, and you have to sort of have some different assumptions and use some different measures and so on.
Okay, thank you very much. By the way, I started to write the sci-fi novel myself, but just for the first chapter yet.
Great.
I love that. I love to hear that. I always want more scientists and more people who know about sloppy models to write more books. So yeah, looking forward to that.
Yes. Okay, thank you very much.
Thank you.
Okay, thank you so much again for your wonderful presentation. And we are all looking forward to your newly published book entitled The World Behind the World. So you have a lot of Chinese readers so looking forward to that book, and we are happy to translate it if you are allowed to under your permission. So we will contact you soon.
That means a lot to me. That means a lot to me. You've been absolutely wonderful, and I'm just so appreciative that you all are working on the translation of my first book and maybe are interested in the second one.
Yeah, the Pharma Club has almost finished the translation for the previous book. Yeah, we are looking forward to the newly book. Yeah, and due to the time limitation, I think the sharing maybe be end now, and I think we are all very appreciated for this wonderful talk. Okay, so because in Chinese mainline it's 10 o'clock, it's over 10 o'clock night here. And thank you again. Thank you so much, Erik.
Thank you everyone for staying up.
Okay, thank you guys. And I think today's sharing is the end. Professor Zhang.
Okay, thank you all of the speakers, and thank you for all the audience. Thank you. Yeah. Okay, so goodbye.